So our first presentation this morning is by Tracy Novacek and Chad Shive. Tracy is the manager of the Operations and Pavement Management branch of the Kentucky Transportation Cabinet, has been with the cabinet for 12 years. Tracy graduated from the University of Wisconsin, lives in Georgetown, Kentucky with her husband and 2 children. Chad is an engineer specialist with the Operations and Pavement Management branch of the Kentucky Transportation Cabinet. He's been with the cabinet for 15 years. He graduated from the University of Kentucky and lives in Lexington, Kentucky with his wife and son. Please welcome Tracy.
Thank you, Jerry, and good morning to everyone. I'm going to start out today by showing you what our pavement management system and its expectations used to look like. We built our pavement management system with agile assets in 2004. The initial system contained our project histories and then all of our evaluations. Kentucky has a system of visual evaluation for all of our pavements that goes back to the early 80s. It started as a worst first evaluation system where we would go out and look at all of the worst pavements in the state, but that switched in 2008. In 2008, we began to realize that by looking at only the worst pavements, we didn't have data on our system, so we moved to evaluating our system on a 3-year cycle in order to look at preservation needs. We also look at all of the interstates and all of the parkways on an annual basis. The remainder of the system is on a 3-year cycle. From that system, in our pavement management system, we kept our visual pavement evaluations along with our collected IRI on the system, and we produced pavement condition reporting, pavement priorities, and did all of our HPMS reporting. By 2013, we had acquired 3 vehicles from Manley that were equipped with laser crack measurement system. What that gave us, along with IRI, was rutting, faulting, all of the laser crack measurement data, photo log, and miscellaneous asset location. So with that came 2 new products for the pavement management system, and that was our photo log viewer, and we started doing some sign inventory. That was sustainable enough. But the data that we started getting from the Manley vehicles started to become more well-known around the cabinet, and we soon started getting more requests for data, and we had more expectations. So when that happened, we soon realized, after a couple years of collecting those full data sets from those vehicles, that we needed to add operator certification. Our operators, all of our data is collected in-house. Our operators had a lot more expectation than they did when we just collected IRI, so we had to add operator certification. We also soon started choking on all of the data processing that was required out of those vehicles, so we had to add a data management plan. And then we started getting a couple more products that people expected. Our division of design started using our data to do MEPDG design calibration, and our universities started using our data for investigation. And then MAP 21 came along, and now we're expected to do MAP 21 reporting. And in order to support an asset management-based decision-making, we have to provide pavement condition forecasts and investment scenarios. So what do we need to add to our pavement management system? Well, just a couple things. We need to add better costs, risk, decision trees, life cycle cost analysis, and more state-specific pavement deterioration models. When we sat down and looked at this, we realized at the end of the day, all we have to do is completely transition to a new data system, rewrite our pavement management system to take that data, implement state-specific modeling, and then create new reporting. So we can do that, yeah. Luckily, we were given a partner with the University of Louisville, and they came in and sat in on all of our strategy planning sessions where we broke down where we wanted to go and the projects we need to do to get there. We began that partnership in the fall of 2013, and they were perceptive enough to see that building a new pavement management system with all of the modern expectations requires a lot more than a core group of engineers. So they built us a team that included not only civil engineers, but also industrial engineers and computer programmers. One of our main projects that we started with them that we're going to talk about today is a process to map our LCMS data to our legacy data. So let's talk a little bit about the legacy data. The equipment to collect that data is pictured on the side. We have been fortunate at the Kentucky Transportation Cabinet to have a group of pavement engineers that have been together for over a decade now at this point. There's a lot of experience and a lot of knowledge there. We are very good at collecting the visual evaluation distresses for our pavements, but we are still just people, and it is a subjective system. How we collect the data, we go out and we survey sections of pavement that are broken by contract history. We collect a variety of different distresses: wheel path cracking, unraveling, transverse cracking, some general appearance scores, and we do that based on an extent and severity system. And then we pair that with some measured distresses, such as IRI and rutting, and we also project a year of needed treatment for each of the pavement sections. And that was historically how we collected the data. And then the lasers came along, and they took our jobs. They are better than us. They provide us with a lot more detailed information. They are more objective, and we get quite a lot of data from the laser crack measurement system. We get rutting, macrotexture, all of the cracking, potholes, patches, etc. This has shifted our need. It's taken us off the field a little less, but we've inherited an immense data processing requirement. So what that leaves us with is a data mountain at this point. We have two systems right now. We have a visual evaluation system, which is a low level of resolution for our pavements, but we know what that's telling us. When we look at that system, we know what a good pavement looks like, what a poor pavement looks like, and what a fair pavement looks like. And then when we look at the LCMS data, which is a high level of detail, columns and columns of data, it provides us with a lot of detailed parameters, but how do we tell the story of our pavement condition? And if we transition fully to LCMS, we let go of all of that historical data that we've collected. We let go of our state-specific modeling, and we lose that ability to bridge between what we had and what we have. So we partnered with the university, and they are working on creating that bridge so that we don't lose those years of data that we have. And Chad's going to come up and talk a little bit about that study.
Thank you. Okay, so Tracy mentioned we had a data mountain, so now we have to attempt to climb it. Our partner U of L has been a great partner. I don't know about you, but my one undergrad course in statistics is not sufficient to analyze this data and actually get us in a place we want to be. So that team has been great in moving us along. So I'm going to cover a little bit about the pilot case study that they did for us to actually transform our LCMS data back into a version that we can use for our current pavement management system. Looking forward. So Tracy covered a bit about our old visual evaluation system. We have 10 criteria, varying scores, integers of 0 to 3, 0 to 5, 0 to 9 for extent severity. Then we're moving to a system that has a great many fields, with numbers of, severities in the inches and extents of cracking in the feet and so forth. So we have to find a way to relate that data to our legacy data to try to keep some historical data flow going. Way too much data. Okay, so LCMS, if we turn on every reporting field, I think there's 176 fields that get reported out of this software. And so what do we do with that? What does fatigue cracking low 180 feet in a 10th mile really tell us? So we sit down with U of L and also with Manley and tried to come up with, okay, what do we need to do to transform this data back into something we can use? So there are a few things here. we wanted to look at what factors actually influence our visual indexes. So for wheelpath cracking extent, what LCMS factors actually would relate to that distress. Then we have to clean up our data. So we're going to use a clustering analysis to verify our data integrity. And then once we have a clean data set, we're going to use factorial analysis to actually find significant variables. So we pick 10 variables that we think fit wheelpath cracking extent, but really only 5 of those are significant, that kind of thing. Then some other options were principal component analysis, and then finally regression modeling. So we sit down with U of L, and they actually proposed a formal approach. So we have factors identification. So we have to identify what factors we're going to use and what is significant for our visual evaluation system. Then data consolidation and processing. So we have to clean up our data. Data quality check. Tracy mentioned that we as evaluators and engineers, we're certainly not perfect. We make mistakes, anywhere from misrecording data to the sun was in a bad angle and we didn't see that crack, that kind of thing. So we have to clean up our data and make sure we have good data that we're using. And then finally, factorial analysis using analysis of variance, or ANOVA, and then linear regression modeling for data mapping. Something here. Here we go. Okay, so first off, factor identification. Okay, like I said, we sat down with U of L and actually Mandalay on the phone with us, and came up with, for every visual evaluation distress that we currently rate, what fields might go into that data set. So from LCMS, we came up with every possible thing we thought might have any significance to wheelpath cracking extent, and then the same thing for wheelpath cracking severity, and all the way down the line. And they weren't exclusive. We could have one data column that might influence 2 or 3 criteria. So we came up with this anything possible factor identification to try to map that back to our visual evaluation system. Okay, so there's a lot on this slide, so let me go through it here. So once we had those factors identified, we had a data consolidation and pre-processing. So there were 2 thoughts here. To summarize LCMS data, we thought we could do an average, so just link-weighted average of every distress averaged over a particular pavement management section, and then that would be the average for that data set. We also looked at what if we talked just about the max data point. So you have a 5-mile section, so that gives you essentially 50 thereabouts LCMS data points. So what if we took, of those 50, the max one? What would that give us? Would that be better than actually averaging them out? So those were the two methods identified for data consolidation. And I've got here, average method, it's a length-weighted average for all the values that cover that pavement management section. And then the max is just the maximum. But 176 fields isn't enough, so U of L said, hey, let's put 2 more in there. So we had 2 additional factors that we thought we might consider. One is a weighted cracking extent, and 2 is pattern density. Weighted cracking extent is, so LCMS gives you crack width, depth, and extent, length. And the cracking extent is bend into low, medium, high for the depth of crack. So U of L thought, what if we weight high cracks, 3 times as severe as low cracks? So we had the weighted cracking extents just 3 times the high extent plus 2 times the medium plus the lows. We wanted to see if that had any significance. And then pattern density. Pattern cracking in LCMS is given by area extent, length extent, and severity. And so we thought, what if we can combine those to actually get a density, which is just length extent, length severity, times 1/12 for a factorless field there, and then divided by area extent. Okay. So data quality. Like we've mentioned, we're not perfect. We have some outliers. We have some errors. So how do we identify those? And how do we identify just mismatched sections? So the university proposed using agglomerative hierarchical clustering, which is a nice big term. It's a fancy way to identify outliers and data issues. You cluster all your individual samples together, you compare that to the LCMS data, and build a nice pretty chart like this. So you should see when you do this a lot of low severity distresses to the left, and then building up towards the right with highs. And if you can see those little arrows in there, those are either 0 points or low comparative or relative numbers versus the rest of the data. And if we go and identify those, that very bottom line there in red shows that we gave a 0 wheelpath extent in this example to a section that probably shouldn't have been a 0. There's quite a bit of all those different types of distresses there identified by our LCMS vehicle. So we continued this for all of our data, threw out the outliers, found issues with all the data, and gave us a clean data set to work with. Okay, now we finally have a clean data set. Now we're looking at factorial analysis. So we have to take all of those factors that we identified at the start, throw in all of our clean data, and actually figure out which of those factors are really significant. So this looks at the factors that we identified, and actually, based on the data, gives us a rating as to whether they're significant or not. And that's the low p-value there. So we're looking at anything with a p-value of less than 0.05. And this is based on, I think, in SAS, if you're familiar with that software. And then that's once we use that analysis, that's going to give us an R-squared value to see how close that data actually fits. And then once we run it the first time, we continue to remove factors with large p-values until we get finally an equation that's just based on values that are significant. Okay. And so this is just an example of the wheelpath cracking extent. And if you can see that, there's our 10 or 11 factors we initially identified. And you can see on the very far right, highlighted in red, there's only 4 of those that the software said was actually significant. And for this one, there's an R-squared value of 67%. And then if we run it again with only those significant values, we get an R-squared value of, I guess that's 68 or 67. In any case, this is the function we want to use because the software tells us it's using only significant values. This is another example of the same thing, and this one is for wheelpath cracking severity. This one, however, we're looking at our 2 different methods. So we said we were either going to use an average method or a max method to summarize our data. So the first slide here is showing excuse me, the max method, and so we've already identified our significant factors here. For this one, we have an R-squared of 55% for the max, and then 68% for the average. So in this case, and as I'll show soon, the average method was the better option here. And so this was done for all of our distresses, for all of those factors we identified, and we finally came up with for wheelpath cracking extent, wheelpath cracking severity, other cracking extent, other cracking severity, and raveling extent, which are some of the factors in our old visual evaluation system. For all of those, the average method was the best. We also have an appearance score in our old visual evaluation system. This is essentially just an overall, what's the pavement look like, 0 to 3 kind of thing. For that one, the max method actually came out to be the best option, which kind of makes sense based on how we do our appearance score, which is based on essentially the most severe factors on the road. So that's what we've come up with as far as a method for each of these visual evaluation criteria. Okay, what's left? Next step. So this was a pilot case study of one road, 43 miles, I think, 80 different pavement management sections in both directions. So what's left is larger data samples. So shortly after our last meeting with U of L, I sent them then every data point from 2015 and 2016 testing. So they went from maybe 8,000 records to 500,000 records. So they're going to start working on that for us. Ordinal logistic regression to output dependent variables as integers instead of what we're currently doing. So we're going to take a look at that. And then using clustering analysis to develop separate regression models for various clusters. So right now we're looking at the entire gamut of 0 to 9 in our old system and trying to get one model for that entire pavement. I guess all the pavements that fall in that category. Now we're going to try to look at, okay, what's the model for pavements that are maybe 0 to 5 years old or 0 to 10 years old, that fit maybe that lower end of the range, and then we need a model to maybe fit those older pavements or those more distressed pavements or quicker distressing pavements. And then that's the last thing there on the different models from newer pavements versus older. Okay, so that's our pilot case study. Like I said, we've really enjoyed working with U of L. They've been a great help to us. And now Tracy's going to talk about prioritization.
Now, after we get the data transitioned from the LCMS source, we still have to take that condition data and turn it into a prioritization system for our projects. So our existing project prioritization system provides us with a composite index for each section of pavement, each pavement management section. And that composite index is decades old. It provided us with a system that gave a large emphasis on the roughness of the road. So what that did for us is it gave us sections of road that could be fully distressed, large severity of wheel path cracking, lots of transverse cracks, open raveling, but it would never travel up our prioritization system because the ride would stay in the 70s, in the 80s, and it just couldn't compete. So our roadways that were on sound engineering road beds would never travel up our system because they just simply would never get rough enough. So we sat down with the university while we're opening up the pavement management system, while we're transitioning to data sources. Let's look at our composite index. Let's figure out how to make a more objective composite index. So they took us through a process called the analytic hierarchy process. It's a structured technique. It's used by a lot of corporations to make decisions. It's an analysis that allows experts to provide feedback on relative importance amount factors that are under consideration and assigns proper weight to the criteria you've selected for prioritizing your projects. What that means is you sit down and create a matrix. So we took all of our pavement experts, we sat together and we were given this as a guide. We listed our criteria that we wanted to use for our composite index, and then we were given this system, and we had to create a matrix. So in this example, on the left, we have wheel path cracking extent, and we have raveling extent. That's what that indicates on the right. And what we're saying is wheel path cracking extent of 5. So we're saying that wheel path cracking is strongly favored over the extent of raveling as far as what drives the deterioration of our roads. And that's just an example. We sat down as a group and we looked at all of our distresses that we do for the pavement, and we discussed which ones drive the deterioration over the others to try and create a prioritization system that is based more on how the pavement is deteriorating and what is driving that need for replacement over just roughness. This was the product we submitted to the university. It looks like just a matrix. It involved many hours of being stuck in a room, arguing, insulting, and threatening each other. And then there was also a cooling off period where we came back together and finally produced this. This gets sent over to the university. They perform their magic. I don't know what happens to it. And it becomes a new weighting system for all of our distresses that we have under consideration. In the end, what it provided us with was a new composite index that rates all of our pavement management sections on a 0 to 1 scale. We took that data and then did a pilot study to compare our old project prioritization system to the new one to make sure that it didn't throw it completely out of whack. And what we found is that the system does successfully address the overemphasis of IRI that existed in our system and now allows those sections that have a lower IRI. IRI is still weighted in our system, obviously. It's just not as heavily as it was before, and it allows something that's heavily distressed to travel up, even though the ride may remain smooth. So from that, we have deterioration models specific to the state. We are transitioning from our old system to LCMS data, and then we are using that data to do a more objective system of project prioritization. But there is still work to be done on the system.
I will finish this up here very shortly. What is the future of our pavement management system? So now we have LCMS data, and we have a process through the university. We're going to have functions to map that data back to our old visual evaluation system version of it. And so now we're going to take that functioned, modified LCMS data, combine that with our construction data, create our condition table. So from there, we can then use the new AHP method of prioritization and also include the models that we already have based on our old visual evaluation system, and then an optimized analysis and output a work plan that would hopefully take all these factors into account at this point. We like to certainly thank the U of L team, Dr. Bai, Dr. Sun, Guanyang, Prajwal, and Payu for their extensive help on transferring our system into the hopefully 21st century. Thank you all. We'll entertain any questions, certainly. So the question was, what do we do to analyze thresholds of pavement structure? Was that?
Structural integrity.
Structural integrity?
The structural integrity.
Okay. Right now, our evaluation method is mostly surface distresses. We have, I guess, a very small coring project in place. Do we do just quarters?
We're just coring project specific
Yeah.
for the
So project specific for coring, but no FWD or anything like that. No. Does that answer your question? And another one? So the question was, we compare LCMS automated distress versus visual evaluation, and do we compare then also the indexes? And the answer is no, because we do not have an index developed for LCMS yet. So I didn't mention that, but so right now our method is to transfer the LCMS back into our old rating system. The next iteration would be then to move directly to LCMS, create an index and models for that system. That's in the next version of this. Yeah.
In your coming iteration model, you will predict each distress or predict the component index?
Right. So the question was, do we predict each distress or an index? Right now we predict each distress.
So do you have any report available for this pilot study?
So the work U of L did is going to be a TRB paper and I think a presentation for the upcoming TRB meeting. And it's possibly going to be published, but we don't know where yet.
They do have papers. They published one for the International Conference on Managing Pavement Assets.
So you want to say that?
Sure. They did publish a paper for the International Conference on Managing Pavement Assets as well.
So our data management plan, we have several things we look at. One is the raw data, raw output from LCMS, which comes in binary or proprietary files, I guess. Two is the photo log data. So right now our plan, excuse me, we're keeping images back as far as 7 years. Years 4 through 7 are reduced quality, reduced size. For our raw LCMS data, we're only keeping it until we process it and then make sure that processing is correct, essentially. So we're keeping it for about a year to a year and a half after it's collected. So we process it, make sure it's good, then we delete the raw data, the raw output from the LCMS system.
And how much a year total?
I'm sorry, I don't have that quantity right offhand, but I do know we're storing right now around 180 terabytes is what we have as a chunk to store all this data, and we're moving some data off as we're putting new on. And we expect somewhere around 200 terabytes is what we can, we actually have to maintain forever, you know, to do this process. So the question is, for LCMS data, did we actually throw out any segments that maybe didn't match the rest of the segments? And then I guess question 2 was, did we have a range of appropriate R-squared values, or what we considered good?
What percentage of data did we throw out?
Or percentage, yeah. So actually, I'm not sure I can answer your first question. I think that would be a more technical question for the U of L team.
It was surprisingly large, though.
Yeah. Yeah, I think I may have to defer that one. If you want to know, email me and I can try to find out. But I know we threw out data. I don't know how much. As for the second question, so the pilot study was only a very small segment. It was 40 miles, 40 centerline miles of parkway, and only 1 year's worth of data. So the point of it was really to develop a method and to I guess make a first run and develop some best practices, you know, to move forward. So some of those R-squared, I don't know if you could see them, but they were a little low. And I think a lot of that was just due to not having enough data. And actually, one of the slides I had up, I didn't cover it, but there were only 2 significant factors for, I think, wheel path cracking severity. And U of L, even in their report, said that that's probably not enough, and that would really require more data to be a valid model. So that pilot study really was just a pilot, and we're going to throw a bunch of data at it and hopefully clean that up. So.
Okay.
Thank you.
Thank you, Tracy and Chad.